All right, we're gonna talk about something really cool today. Um, we talked about Euler's method in the last lecture, and that was a method of approximating solutions to initial value problems. That's cool and all, but we saw that even with reducing our step size to half what we did in the initial example, we had a lot of error and it tended to pile up really quickly. And it turns out that Euler's method's a pretty not that great method of approximating solutions. So why do we talk about it? Conceptually, it's easier to think about walking along a tangent line. It's not readily apparent how you could do better than that given the data. And I think that that's a really interesting thing. Even if you understand differential equations really, really well, how can you better predict what a solution is going to be if all you have is the knowledge that a solution passes through a particular point? How do you do it? And it turns out there's a whole bunch of better approaches that we can do. And while they aren't immediately obvious, I think that what we talk about today is going to be like, oh, cool, that's really neat. I love this material. It's a little more challenging, but I think that we can get it together with a little bit of graphs and I don't know, some discussion and stuff. So hopefully it makes some sense as we get into it. Why don't we get into it? So the first, as I said, there's a bunch of different methods. The first one we're going to touch upon is called the midpoint method. The midpoint method is a method that does not use the tangent slope at the initial point to advance, but it does use that slope as something, okay? We use that slope, the same one that we would use with Euler's method, except as a guide to send us in the right general direction to start. But that's not what's going to help us to land anywhere. Basically what it does is it tells us in what general direction to go, but then we actually use information from later on in that journey to estimate which direction we should go. It's a little bit interesting, but I have a couple of good analogies, or at least one that I'm going to share with you that makes a little bit of sense. Okay, so what we do is we check the tangent line at the current spot, at the initial condition, as we usually do. And instead of going a whole step in that direction, we stop halfway between t0 and t0 plus h. And what we do is we remember that the differential equation has an infinite number of solutions that fill up the solution space. So that means that halfway, if I go halfway along that path, there's going to be another solution that passes through the point that's right there. So what we do is we look at the slope of that solution curve and we take that slope. We go back to the starting value and use that slope to advance. Kind of weird, okay? Let's draw a little bit of a picture of what's going on. I'll just use the same like kind of fan of different solutions that we talked about before. So maybe we'll draw some things that look like this. All right. And maybe the one that we're interested in, the solution that we're interested in is this one. Whoops. Sorry. I'll draw the one that we're interested in say green. This is maybe the one that we're interested in actually approximating. So we have our t0 and y0 right here. All right. And so what we do, so there's a whole bunch of different solutions, but that green one is the one that is the solution to the initial value problem. That's the noodle that we're interested in approximating. And so Euler's method, we found, often produced a lot of error as we went forward in time. So this here is t0, t0 right here. And suppose here's h. What Euler's method would do would be to take this approximation right here, using that tangent line, and say, hey, this right here is the new estimate, which is already way off that green curve that we're interested in. That's not what midpoint method's doing. What midpoint method does is it walks half a step forward to this spot right here. Oh, sorry, this is t0 plus h, I guess. It walks halfway, looks at this point right here, And then that's not our next estimate. It looks at the slope to whatever solution goes through that point. Now, if the solutions can change kind of continuously, which is often the case with these simpler differential equations, then the tangent slope there is going to look something like, it's going to be close to what's up there on the other curve. It's going to be something like this. All right, so we're going to use that slope, this tangent slope with a bit of a greater slope, I guess. I'm going to return to the start, and I'm going to use that slope to advance. So I'm going to try to draw a line that's parallel to that one. That looks like it's about, let's see, here. That looks like it's about parallel right there. All right, and I'm going to take a step forward along that path from the beginning. And that's the slope that I derived from that half step forward at that point. And just look at this. Just look at this. Like, this was accidental. I didn't even mean to do this. At t0 plus h, on that line, this here is the estimate. It's almost right on the curve. Of course, it's going to depend a lot on the kinds of functions that are involved, okay? So let's try to write down some things, because I think that it's the sort of thing where it's a process that I want to talk about, that I want you to see all the steps of it, and it's like a graphical, like marrying the graphical approach with the words I'm saying to make sure that it makes sense. So we take half a step forward. So first, take half a step forward along the usual tangent slope, and take the so I'm going to say find the tangent slope to the solution that passes through that point. So the find the slope of the solution that passes through that point, right? And that goes back to our very first conversation about direction fields and differential equations. There is a solution that goes through this point, and it's going to be something that probably looks, like this, right? So I'm looking at the tangent slope right there. I'm going to get rid of that just to make sure that that's, it's already cluttered enough, right? So then, second, return to the start and use that slope to advance to t equals t0 plus h. And so that's the path we walk along. That is the path we step forward on. Okay, so that's I have 2 steps. I'm going to say this is step 1. This is step 2. So we're going from here to there. What you want to think about this as is like, okay, imagine you're going through and you're trying to find your way along a forest path and you have a blindfold on, okay? Maybe you get to glimpse at the road below you and say, okay, based on what direction the road is going right now, I can walk straight in this direction and hopefully I'm not far off the path. But if the path is a curve, then you're going to find that you go off the path. What midpoint method is doing is it's bringing a friend along with you. It's bringing a friend along with you, and what you're doing is you're doing the same thing. You're sending them forward as a guide. You're sending them forward, and then they're going to stop halfway to the next step. They're going to look at what direction their road is headed at that point, shout back at you, and say, you know what? Go in that direction. And you're going to follow their advice and walk in that direction. So it's this 2-step process. And it's more complicated, right? It's challenging, but I think it makes some sense. So 2 steps. First, send a guide forward. They stop, check a slope, report the slope back to you, and then you use that slope to advance rather than your slope. That's how it works. And it turns out that this is a whole lot better. So that was really funny. I just got a call from my family, and so that's going to become a little beepy issue right in the middle of my video. So my apologies for that, but that's all right. That's going to be an interesting little diversion here in the middle. Okay, so let's talk about what we just did here. The midpoint method is what this is called, and it is a two-step Runge-Kutta method. Runge-Kutta. A Runge-Kutta method is basically it's named after a couple of mathematicians that did some work on this problem. I didn't know how to pronounce this word. I had to look it up a whole bunch, and I've heard like people say Runge-Kutta. I've heard Runge. It seems like Runge-Kutta is what most people pronounce it as, so that's what I'll say right here. And yeah, it tends to produce way more accurate results than straightforward Euler's method. So let's put this all into mathematical terms, because that's what we need to use at the end of the day. These two steps are going to be things that we want to codify into some actual algorithmic steps here. So we want to be able to actually do calculations that involve these things. So suppose that we have the same sort of IVP that we had before. So we have y prime equals some function, and then we have y of t0 equals y0. The scheme looks like this. We're first going to define, we use k's here. You can use whatever you want, but I like k1, k2, and so on. We want these two steps. The first thing we're going to do is define k1 equal to h times f of t0, y0. So this tells us how much of an increase in y we would get if we were to simply use Euler's method, because that's the first thing we do. We're sending that guide forward on the usual tangent line that we would step along for Euler's method, but we're not actually using that to get to our estimate. What we do is we now define a second k. We take that, and we define it as h times f of t0 plus a half h, so half a step forward in time, y0 plus a half k1. So that's going to be halfway up the line that we'd usually walk at. And notice that f of this is going to give us the slope of that line. And therefore, this is the check to see what the slope at that point is. This is what k2 is, and it's important that we calculate that correctly. This tells us how much y would increase if we instead use the slope at the midpoint of the line segment from Euler's method. Okay, we're going to use that slope and step forward. So we're going to let y1 equal y0, the old y0, the original, the initial condition, plus h times that slope. And that's what our next estimate is. So we have this two-step approach instead. And that's going to kind of codify that series of steps that we would need. And of course, T1 is just a time step forward. And then you repeat the process. You always, at every single step, treat the current pointer at as kind of the new initial condition of some sort. And then you have these two steps. Send the guide forward, have them report to you what slope to take, and then use that slope to go forward. And it's the same scheme again and again and again. And it looks like this. So we have that K1, our first little estimate is h times f at the point we're at. K2 goes halfway there and reports the slope at that point. And then h times that gives me the tangent, the tangent line, essentially, the amount that we would increase if we walked along that new tangent line. And so that's what we take. The new estimate is equal to the old estimate in terms of y, plus that second piece here, that K2. So we're going to use this on an example here, and we'll see. It sounds really complicated, but I think that in practice it's not too bad. I'm going to use the same example that we did for Euler's method, so we can see the improvement pretty easily. And then you can compare the two methods as well. So, yeah, let's do this. Y prime equals y plus sine of pi t, that's our f. this here gives us an initial condition that is t0 equals 0, y0 equals 1. We're using midpoint method. So that's this two-step approach, and our h is 1. Okay, we're starting at t equals 0. We need to get to t equals 2, so we need to do this twice. That should be good. So let's do this. We're going to start with our t0 equals 0, our y0 equals 1, and we need to calculate, right? It's not just one thing. We need to do two things. So let's do that. Our k1, our first estimate, that tangent slope forward is h times f at t0, y0. So it's 0 and 1. And if we were to write that down, we get k1 equals, our h is 1, so that's nice. And f of t0, y0 is, let's see, 1 plus sine of pi times 0. And so you work that out, that means that k1 is equal to 1. Because sine of 0 is 0, 0 plus 1 is 1, 1 times 1 is 1. Okay, that is going to be a quantity that I then use to calculate k2. And k2 is going to be h times f of, and now we go half a step forward, 0.5, and we take y0 plus a half k1. So it's going to be 1 plus 0.5 times that 1. Whoops, I want a round bracket here. So this here, I just want to make it clear, this is y0 plus a half k1, just like this. Cool. All right. And so we want, basically, this is a 1 times f of 0.5 and 1.5. That's what we're interested in. So we're taking the tangent at that other point, basically. And that's going to be, let's see, 1 times, and then we have 1.5, looking at the f, plus sine of 0.5 pi. Sine of 0.5 pi is sine of pi over 2. That's 1, so we get 2.5. Right? If you're going to shove this into your calculator, make darn sure you're in radians mode. That's just an assumption. And we had a couple of people in the last test that forgot that trig is in radians for, real math, I guess. Cool. All right. So anyway, this is 2.5, and I'm going to take this, and we're going to get a new estimate. Y1 is equal to y0 plus that k2, and that means that we get y1 equals, let's see here, the old y was 1 plus 2.5, or y1 equals 3.5. Excellent. Okay, so we get y1 equals 3.5. This is our estimate at t equals 1. So we need to do this one more time to get an estimate of what's happening at t equals 2. So let's see. That's the first step. And now we have t1 equals 1. I'll step forward. Our y1 is equal to 3.5. Okay. And we have to go back and calculate those two estimates. It's like starting all over, but with one more iteration here. So k1 is equal to h times, and then f of what we're at. So that's 1 and 3.5. And so that's going to be, let's see here, 1 times, and then 3.5 plus sine of 1 pi. So sine of pi. I do believe it's y plus sine of pi t, so this seems good to us. And sine of pi is 0, so I think we get 3.5. Okay, k2 is going to equal, let's see here, it's going to be h times f of, okay, I need to go half a step forward, so I'm not at 2, but I'm at 1.5. And then I need here 3.5 plus a half of the k2. So that's this here, let's just remind ourselves where this came from. This is the previous, so y1 plus 1/2 k1. And this is the K1, that's 3.5. Our Y1 was 3.5. So 3.5 plus a half of 3.5 is 3.5 plus 1.75. I think it's 5.25. So, and the H is still 1. So we get 1 times F of 1.5, 5.25. And this is going to give us 5.25 plus the sine of 1.5 pi. That's 3 pi over 2, which is negative 1. So I think we end up with 4.25. Then finally, so that's our K2. And so our Y2 is going to equal Y1 plus the K2, which is equal to what we had. The last one that we had was 3.5 plus the 4.25, and that winds up being 7.75. Here, I just want to rewrite this a little bit so I have some room. 7.75. That's going to be our final estimate. I just want to rewrite this formula so I have it right. This is Y1 plus a half K1 rather. And that 7.75 that we calculated there, that is our estimate. This is our estimate at t equals 2. And you'll notice that, this is going to be a lot closer to that. We had the true result that was reported in that last lecture, and we're a lot closer to it than we were using Euler's method. And I just want to remind you too that this is using a pretty big value for h. We're taking big steps forward of 1 unit at a time. If you were to shrink this down, you'll get a whole lot better too. So, yeah. So in any case, the relative error, if you were to calculate it using the same solution as before and so on, has fallen to around 20%, and that would decrease much more quickly as well if you were to continue to reduce that step size. But there are a lot of calculations involved and so on. So, as I said, this is what's called a Runge-Kutta scheme. And as I said, it's named after a couple of mathematicians, Karl Runge and Wilhelm Kutta. I don't know if I said that right. I probably butchered their names and so on. But this is about a 100-year-old strategy to approximate the solutions to IVPs, initial value problems. And this is only one such scheme, right? This is the simplest one. In general, there are multi-step schemes that use all sorts of different estimates and then take kind of an average of them. And we're going to talk more about those in the lectures to come. So let's bring it in here. I hope this made some sense. I know that I had that weird a family call and some beeps and then I got an email. I always try to close my tabs ahead of time so that I don't have sound coming from my computer. And I didn't realize I had 2 email tabs closed or open. So I closed one, but one was left open, and then I got the notification, and my sister tried to call, probably to tell me something about my niece and nephews. I'm a human being too, and I've got other parts of my life. So getting these lectures done, super important. But I apologize for interruptions here and there. I just don't want to refilm all the time because it's very time consuming. So I appreciate your patience with me and in my life. Anyway, hopefully this made some sense. I love this stuff. I think it's really, really cool. I think that the idea of producing later estimates using data that's not actually stuff you have, but stuff that's to come is just really, I don't know, big brained. I love it. And I think that it makes a lot of sense when you look at the pictures that are involved. So I want you to work with that, to be right on top of some of those exercises so you can be confident that they make sense too. Because you're going to want to get that 2-step process that we just covered here before you try to go crazy. Because the next thing we talk about is going to be 4-step processes. So we're going to be talking about a Runge-Kutta 4 scheme in the next lecture, and various other schemes that involve many different estimates and combining lots of information. Basically sending out an army of guides forward all of whom are going to yell back at you which way to go. And you're like, oh, which way to go? So I'm going to kind of take a combination of all of you and then use that to go forward. Pretty cool stuff, but practice and let me know if you need any help. All right? So ciao for now, and I will sign off until next time. Have a good day.